Hello, everyone, and welcome back. In today's episode and in tomorrow's episode, we are going to be talking about an algebra skill called partial fraction decomposition. We're going to use this algebra skill to help us to expand the number of functions where we can take the integral using fundamental theorem of calculus. We will be using this skill in the final episode of this class to help us to integrate some separable differential equations that show up in real-world applications. And partial fraction decomposition is also used pretty heavily in the math class called differential equations, here Math 238. So what is partial fraction decomposition? Partial fraction decomposition is the process of rewriting a complicated fraction as a sum of simpler fractions. To give you a quick example of what I mean, suppose that I had the fractions 1 over x plus 3 and 1 over x plus 2. If I used the process that we learned in algebra for how to add fractions together, then I would need to take those two fractions and establish a common denominator for both fractions and convert each fraction so it had this common denominator and then add the two fractions together, which would in this situation give me 2x, 2x's in the numerator, and a 5 in the numerator as well. What partial fraction decomposition will do is it will give us a way to take a complicated fraction that looks like this one on the left and rewrite it as this expression here on the right, two simpler fractions added together. And the reason why we might want to do something like that is that this very complicated fraction on the left would be very hard to integrate, wouldn't it? But each of these simpler fractions on the right would be easy to integrate, just using a very basic u substitution and the integral formula corresponding to natural log. So partial fraction decomposition gives us a way to rewrite a difficult fraction that's hard to integrate in terms of simpler fractions that are easy to integrate. Now, in today's video, we are going to be talking about how to do a partial fraction decomposition on a fraction where the denominator contains distinct linear factors. By which I mean today, we are going to be talking about how to decompose fractions that look like this one, where the denominator contains the two factors x plus 3 and x plus 2. Each of those factors is linear because it just contains x to the first power. Additionally, these two factors are distinct from each other. They're different. One is x plus 3 and the other one is x plus 2. This is the kind of thing that we will be focused on today, and the kind of thing that we will be focused on in the next episode are things, for example, like 1 over x squared plus 1, x minus 4. This denominator contains a factor which is not linear. This denominator contains a factor which is quadratic. So that is something that we'll learn how to deal with in the next episode. Additionally, in the next episode, we'll learn how to deal with something like x over x minus 4 squared, because this denominator contains two linear factors, but they are not distinct from one another. It's the same factor repeated in this case 2 times. So these are the kinds of things that we will learn how to treat in the next episode. So to demonstrate the process of partial fraction decomposition on a fraction like this one, where the denominator contains distinct linear factors, let me walk you through the steps using a running example. I will decompose the fraction 1 over x squared minus 5x plus 6. The first step in a partial fraction decomposition is always to factor the denominator if it's not factored already. So in this case, my denominator contains x squared minus 5x plus 6. That's a quadratic denominator. And so to attempt to factor it, I would be looking for a pair of numbers which, when you multiply them together, you get plus 6, and when you add them together, you get minus 5. So the pair of numbers that I can think of that achieves those two goals are minus 2 and minus 3. So this would be the same fraction with the denominator factored. Step number 2, once you have factored the denominator completely, and you've seen that your denominator contains distinct linear factors, the next thing that you're going to do is set up a template for the decomposition. You're going to set up one fraction for each factor in the denominator from step number 1. And in each of those fractions, you're going to have an unknown constant in the numerator. To show you what I mean, in the context of the running example, I have my fraction 1 over x minus 2, x minus 3, which I am attempting to rewrite as a sum of fractions that are simpler. So I'm going to set up a template for the decomposition on the right-hand side, and I'm going to set up one fraction for each factor in the denominator. One fraction with a denominator of x minus 2, and one fraction with a denominator of x minus 3. And then I'm going to use some letters to represent unknown constants in the numerator, an a up here and a b up here. My mission now is to figure out exactly what values of a and b need to live in the numerators of these two fractions in order to make this right-hand side truly equal to this left-hand side. So step number 3 to that end is to take this equation that we've just written down here in step 2 and multiply both sides of the equation by the least common denominator to clear the fractions. So if I copy paste the equation from step number 2, and if I think about what would be the least common denominator of all these three fractions, it looks like this quantity on the left, x minus 2, x minus 3, will serve as a common denominator for all three fractions. So I'm going to go into this equation and multiply both sides of this equation by this LCD. And one copy of that least common denominator is applied to every fraction in this expression, one for this fraction on the left, and then one for each of these fractions on the right. Now that I have written this down, I can simplify and clean up what I have written down by canceling common factors. This x minus 2 upstairs cancels with this x minus 2 downstairs. This x minus 3 cancels this one. This x minus 2 cancels this one. And this x minus 3 cancels this one. And then what is left behind from that process is a 1 on the left, an a times x minus 3 on the right, as well as a b times x minus 2 on the right-hand side. So notice a little pattern here that when we clear the fractions, each term ended up with a copy of what its denominator was missing. So for example, A here ended up next to an x minus 3 because its denominator did not have an x minus 3 in it. And B ended up next to an x minus 2 because its denominator did not have an x minus 2 in it. Okay, now remember that our goal here is to find the constants A and B that make this left side equal to this right side. Our goal is to find A and B. And if you need to find two unknowns, then you need at least two equations to make that possible. So to create the two equations that I need to find A and B, here's going to be my process. The first thing that I'm going to do is simplify and distribute this equation that I've written down in step 3, then set up equations based on the coefficients of the constant terms, the x terms, if you have any x squared terms, etc. Let me show you what I mean, going back once again to our running example. I'm going to start by distributing the equation that I just wrote down. So I distribute a through this expression, giving me a times x and negative 3 times a. And I'm going to distribute b through this expression, b times x and negative 2 times b. Now I'm going to go into this equation and I'm going to consider the x terms and the constant terms separately. On the right-hand side of this equation, the coefficients of x are a and b. And on the left-hand side of this equation, I don't have any x's. I have 0 x's. So on the left-hand side of the equation, my coefficients of x are 0. And from looking at the coefficients of the x terms alone, I have one equation that's telling me about what a and b are doing. A plus b must be equal to 0. If I separately look at the constant terms, on the right-hand side, my constant terms with no x's are negative 3a and negative 2b. And on the left-hand side of the equation, my constants are 1. So looking only at the constant terms, I find that 0 must be equal to a plus b, and 1 must be equal to negative 3a minus 2b. So now this forms a system of equations that I can solve for a and b. So let's call this step 5. Step 5 is solve the resulting system of equations for a, b, if you have it, c, and so on. Now, in this case, I think the easiest way to solve for a and b is to take that first equation and rewrite it to get a statement sort of like b is equal to minus a. If I take that information and substitute it into the second equation, then I find that 1 must be equal to negative 3a minus 2 copies of b, which I now understand is equal to negative a. If I simplify the expression on the right side, I get that 1 is equal to negative a, so a must be equal to minus 1. And if I put that back into this equation here, that tells me that b must be equal to positive 1. Now that I have found the values of A and B, the final step of the decomposition is just to put back these values of A and B into the template that we established back here in step 2. This gives me a composition equal to A was -1 and B was +1. If I have -1 in the numerator over x minus 2, and if I have +1 in the numerator over x minus 3, if I have those two values over those two denominators, then this right-hand side will truly be equal to the original fraction that I had on the left-hand side. Those will be exactly the same function. So now that we've talked about how you can do decomposition, let me talk very briefly about how you can use the decomposition to help you with integrals. For example, suppose that someone asked you to calculate the indefinite integral of this function that we worked with in the demonstration, 1 over x squared minus 5x plus 6. This is too complicated to integrate as it currently stands, but I can use the partial fraction decomposition to rewrite the integrand as something that is much easier to calculate. We saw that this expression in the integrand was equivalent to -1 over x minus 2 plus +1 over x minus 3. So now that we have established that, all that we have to do is integrate each of these terms using, for example, a simple substitution. If you do that, you get negative natural log absolute value of x minus 2, positive natural log absolute value of x minus 3, and then plus c, since this is an indefinite integral. Partial fraction decomposition allows us to calculate these integrals much more easily. Okay, let me show you one more example. And just for flavor, I think I might mix this up a bit and put like a 3x plus 1 in this numerator instead of just a 1. So the first thing that I'm going to do is I'm going to factor this denominator. So recalling from the review bite video, the first thing that I'm going to do is I'm going to factor out the greatest common factor. There is an x in x cubed and there is an x in x, so I'm going to pull out that x first of all. And then I see that that thing that has been left behind, x squared minus 1, can be factored further. And I acknowledge that as a difference of squares. So I can factor that, for example, as x times x minus 1 times x plus 1. So now I have a fraction with 3 different linear factors in the denominator. And so I'm going to set up a template containing 3 fractions on the right-hand side. X, x plus 1, and x minus 1. And I'm going to put a couple of unknown constants in each of these numerators, a and b and c. And my goal is to figure out exactly what values I need for a and b and c in order to make this left-hand side truly equal to this right-hand side. To that end, I'm going to multiply both sides of this equation by the LCD. So each fraction gets one copy of this quantity x times x minus 1 times x plus 1. Now let's clean that up and see what's left behind. This x cancels this x minus 1 cancels this x minus 1, and so on And what is left behind from that process is a 3x plus 1 on the left, an a times x minus 1 times x plus 1 on the right, plus a bx x plus 1, plus a cx x minus 1. Now we simplify this result and distribute. So on the left side, copy paste 3x plus 1, multiply all of this out, and I get ax squared minus a. Multiply out this second expression here, and I get bx squared plus bx. Multiply out this expression in the back, and I get cx squared minus cx. Now I'm going to look at all the like terms in this expression, starting, for example, with the x squared terms. If I look at the coefficients of x squared on the right, I have a and b and c, all positive. Meanwhile, I have no x squared terms on the left, so all of that together would equal 0. Let's do the same thing for the x coefficients. If I look at the coefficients of x on the right, I get b and minus c. And on the other side of the equation, my coefficient of x is 3 units. And if I look at the constant terms, let's use yellow for that, constants, then I get negative a on the right and positive 1 on the left. So now I have a system of 3 equations, which is what I need for 3 unknowns, and let's use method of substitution, for example, to help us to solve this. The first equation immediately tells us that a is equal to minus 1. And if I put that information into the first equation, then that tells me that 0 is equal to minus 1 plus b plus c, which means that minus 1 is equal to b plus c. Now suppose I rewrote this equation and isolated b from that. If I put that information into the second equation, here in blue, then that tells me that 3 must be equal to negative 1 minus c minus c. And from that, I get 4 is equal to negative 2c, which means that c must be equal to minus 2. And finally, I can substitute that back into this equation to find the value that b must be equal to. B must be equal to minus 1 minus negative 2. The value of b is positive 1. So having found the values that I need from a and c and b, then all I have to do is go back into this template that I set up earlier and replace those values of a and b and c with the values that I've just found. A is minus 1, b is positive 1, and c is negative 2. And so this expression here on the right side would be the decomposed version of the original complicated fraction. Now that we know how to rewrite this complicated fraction as a sum of simpler fractions, then all that we have to do, if we were asked, for example, to integrate this guy on the left side, is to rewrite it, first of all, in terms of its decomposed version on the other side of the equation. And once again, this can be accomplished using just the integral formula related to natural log, as well as a couple of u substitutions for these second terms here. Negative natural log of x, natural log of x minus 1, and negative 2 copies of natural log of x plus 1 plus c. Quick correction here, I noticed I made an error. So sign error happened right here when I was rearranging this equation. Minus 1 on the right side would become positive 1 on the left side, which implies that b is equal to positive 1 minus c. And from that, if I plug that upstairs here, I find that b is equal to positive 1 minus c minus c. So that turns this 4 into a 2. That turns this c value into a minus 1. And so that turns this b value into b equals 1 minus negative 1. So the value of b should truly be 2. This would be 2, and this would be minus 1. Quick correction there, which would of course manifest into the value of the integral that we calculate later on. Here's 2, here's minus 1, here's 2, and here is minus 1. Now, the process that we just went through, the 6-step process, can get a little long and a little time consuming, especially if you're dealing with a fraction that has a lot of factors in its denominator like this one. So I'm going to record a separate video that shows you a special shortcut method that can be used in cases like this, a method that is much, much faster than what we have done so far today, that will allow you to find the values, for example, of a and b and c here really quickly without having to clear fractions, without having to solve a system of equations. It's very fast. So if you're interested in seeing the shortcut, I invite you to watch the supplemental video that will come right after this one in the playlist.